Okay, so in this video, we are going to prove that the dimension of a vector space is well defined. So here's the premise. We have a vector space V, and B is a subset of V. So B is a collection of vectors in the vector space V. And we say that if you remember, B is a basis of the vector space V if B satisfies two conditions. First, the span of B, so the span of the vectors in B, gives all of the vector space V, and the vectors in B are linearly independent. And if you remember, this means that the vectors in V are generators of the entire vector space, and because the vectors are linearly independent, this guarantees that the generating set B is as small as possible. And if you remember, if we have a basis of a vector space, the dimension of the vector space we define to be the number of elements in any given basis. And you think, well, there is something that could go wrong here. What if, say, you find a basis of a vector space V, and I find a basis of a vector space V, independently of U? Is it possible that we somehow find two distinct bases that have a different number of elements? And if that's the case, then our dimension would not be well defined. What we're going to prove is that any two bases of a vector space will have the same number of elements, which proves that the dimension of a vector space is actually well defined. So here's the theorem. So we are going to assume that we have two bases of the vector space V. So the first one, say B. So suppose that the basis B contains the elements U1, and here I'll be lazy, I won't write the little arrows above each vector, but they are vectors, so U1, U2, and suppose there are n vectors, Un, and let's take another basis, say B hat, equaling now, let's call them V1, V2, and again those are vectors, up to say Vm. So let B and B hat bases of V. So B and B hat be bases of V. Then what we're going to show is that n equals m, right? The size of B is n. There are n vectors in B. The size of B hat is m. There are m vectors. And what we'll show is that m equals n. If you prefer, the size of B, which is equal to n, will actually equal m, which is the size of B hat. And this will prove that any two bases must have the same number of elements. Therefore, the dimension of a vector space is well defined. No matter which basis you find, you will always have the same number of elements. So let's prove this. And we know that because B and B hat are two bases, they both have these two properties. Both B and B hat span V, and both vectors in B and B hat are linearly independent. So let's start with the fact that the span of B hat is V. Well, this means that every vector in our vector space is a linear combination of the vectors in B hat. Well, let's take U1. U1 is a vector in V, and so U1 must be a linear combination of these vectors. So there must exist m real numbers so that U1 is a linear combination of the m basis vectors in B hat. So we can say U1 is C1V1 plus C2V2 up to CMVM. And now if you think of it, because B is a basis of V, the vectors in B are linearly independent, so none are the zero vectors. So if every coefficient here was equal to 0, U1 would be the zero vector, and this is impossible. So there must be at least one coefficient C1, C2 through Cm that is not 0. Whichever one it is, we can move it up front, so we can assume that C1 is the one that's not 0. And now, let's isolate V1 as a combination of U1 and V2 through Vm. This will imply that C1 V1 equals U1 minus C2 V2 minus up to Cm Vm. And because C1 is assumed to be not 0, we can divide across by C1 or multiply by 1 over C1. And we get that the vector V1 is 1 over C1 times U1 minus C2 over C1 times V2 minus up to Cm over C1 times Vm. And why is this interesting? Well, V1 now is a linear combination of the vectors U1, V2 through Vm. So if you think of it, we can exchange in B hat the vector V1 with the vector U1. Because as you can see, if you have vector U1 and vectors V2 through Vm, so these vectors, you can generate vector V1, and so you get back the entire space V. So, the span of initially B hat, which was equal to V, is now equal to the span of, and now we can replace, as we have just said, V1 with the vector U1. So span of U1 and V2 through Vm. And as we have just said, the reason why this is valid is if you have U1, V2 through Vm, you can construct with a linear combination of these vectors, you can construct V1, so you lose absolutely nothing, and so you still get back the entire vector space V. And now the idea is to repeat this argument. Because the span of these vectors is the entire space, well, vector u must be expressible as a linear combination of these vectors. And so we repeat, and you'll see where this is going. So this implies that we can express u2, and I will be abusing here the notation. I'll use C1 through Cm again, but they most likely are different coefficients. But u2 is a linear combination of these vectors, as these vectors generate the entire vector space. And so this would be C1 times U1 plus C2 times V2 now, up to Cm times Vm. And now, here's what's interesting. The question is, could it be that C2 is 0, C3 is 0, up to Cm is 0? If these were all 0, then you would have that U2 is a linear combination of U1. Therefore, U2 and U1 would be forming a linearly dependent set. But this is not true by assumption, because we know that B is a basis of the space by assumption, and so the vectors in B are linearly independent. But remember, vectors are dependent if one is a combination of the others. And so if C2 through Cm were all 0, U2 would be a linear combination of U1, therefore the vectors in B would be linearly dependent. Since it's not the case, at least one of C2, C3 up to Cm must be non-zero. Whichever one it is, put it back in place of C2, V2, so we can assume that C2 is the one that's not 0. Now you say, well, as we did before, we solved for V1. Let's now isolate for V2. So C2, V2 will be equal to U2 minus C1, V1, C1, U1, sorry, minus, well, what's here? And this will be C3, V3, minus up to Cm Vm. Since C2 is assumed to be not 0, we can multiply across by 1 over C2, which means that V2 is 1 over C2 U2 minus C2 over C1 over C2 U1 minus C3 over C2 V3 up to minus Cm over C2 Vm. And now look at this. We said that the span of vectors U1, V2 through Vm was the entire space. But if you look, V2 is a linear combination of U2, U1, V3 up to Vm. And so if you think of it, if we replace V2 by U2, we lose nothing. Because if you have U1, U2, and V3 up to Vm, you can generate vector V2. And so we can replace now V2 by U2 and still have a span that is the entire vector space V. So this implies now that the span of U2, whoops, let me keep the right order, the span of U1, U2, right, we have just replaced V2 by U2, and then V3, V4 up to Vm is still the entire vector space V. And then you see we can repeat, right? Initially, we had the set B hat as our basis, which was given by V1, V2, V3 up to Vm. And you see what we did. Using the same argument twice, we were able to replace V1 by vector U1 from basis B, right? Basis B was U1, U2 up to Un. So we used the argument once, and we said that we could replace in B hat V1 by U1, and the span will still be V. Then we repeated the argument, and notice that we could replace V2 in B hat by U2, and the span is still V. And we could repeat now. We could, with the same argument, prove that if we replace V3 by U3, the span is still the same. So if we just repeat, we can fit in all of B into B hat, and the span is still the same. There is one question though. Is it possible that we have more vectors in B than we have in B hat? Right? We are replacing V1 by U1, V2 by U2, then we'll do V3 by U3, and so forth. The question is it possible that we have more vectors in B than we have in B hat? So think of it. If you could replace all of these up to U1, U2, U3, U4 up to UM, and if there were some leftover vectors in B that weren't in our list, this would imply that the set B is linearly dependent. Because suppose that we have more vectors in B than we have in B hat. So n is strictly bigger than m. Then, so this will be the argument, so if n is strictly bigger than m, then after we repeat, we will have that the span of U1, U2, up to Um is still the entire vector space V. But if there were more vectors in B than in B hat, then we know that UN, because n is bigger than m, UN is not in this list. And so now think of it. If that's the case, then because the span of U1, U2 through UM, which is a shorter list than U1 through UN, still span the entire vector space V, and because UN is a vector in V, then UN would end up being a linear combination of the vectors U1, U2 through UM. And this would prove that the vectors in B are linearly dependent. But by assumption, B was a basis. And so the vectors are linearly independent. Therefore, this is not possible. So this gives a contradiction. Well, this means that the assumption that n is bigger than m is false. Therefore, what must be true is that n is, well, what's the opposite of n is strictly bigger than m? N is less than or equal to m. And that's our conclusion. So we have to be able to replace every vector in B by the corresponding vector in B hat, by the corresponding vector in B. So we can replace v1 by u1, v2 by u2, v3 by u3, up to vm by un. So we have to be able to fit all of B into B hat. And now think of it. What if we reverse the roles of B hat and B? So if you go back to the very beginning of the argument, and now in the argument, switch B for B hat and B hat for B, you will get the opposite conclusion. So this is now reversing the role in our argument of B and B hat. We will get the opposite conclusion. That m must be at least, m must be at most n. You see, the argument initially was that we have to end up being able to fit all of B into B hat. So there must be at least as many elements in B hat as there are elements in B. But if we flip the argument, the roles of B and B hat, we will end up proving that we have to also be able to fit all of B hat into B. So there must be at least as many elements in B than there are in B hat. So n must be at least as big as m. But now if you combine these two together, what is the conclusion? Well, n is at most m, and m in reverse, or in return, is at most n. So how can you have an integer m that lies between n and n? Well, the only option is that m and n are equal. But m was the size of B hat, n was the size of B. Therefore, the number of elements in B hat, which equals m, must equal the number of elements in B. And this completes the proof. We have taken two arbitrary bases of our vector space V, B and B hat, and just proved that the number of elements in B hat must be the same as the number of elements in B. Therefore, the dimension of the vector space as the size of any basis is well defined. And this is our conclusion. So it is impossible that for a given vector space, say you find a basis with 3 vectors, and I find a basis with 5 vectors. This cannot happen. No matter in which way you find your basis and in which way I find my basis, they will always have the same number of elements, and so the dimension of the vector space is well defined. One last comment. We have proved the argument that the dimension of a vector space V is well defined in the case of a finite dimensional vector space. We assume that B had a finite set of generators. The surprising thing is this is also true of infinite dimensional vector spaces. If you have an infinite dimensional space, any two bases must have the same size. But then this is a bit more tricky because there are different sizes of infinity. But know this, that it's actually also true. Even with infinite dimensional vector spaces, if you find a basis one way and I find a basis in a different way, they will have the same size, and the technical term here is the same cardinality. But this is a different story. but just be aware that the result is still true even though V could be infinite dimensional.